not the presentation.
Oh, yeah, like this?
Yeah, perfect. Hello again. So now we have the second contributed speech from our abstract. The speaker is Ulysse Rancon from University of Bordeaux in France. And the title of the talk is StereoSpike, Depth Learning with the Spiking Neural Network. And we are ready to listen to your presentation.
Thank you. Thank you so much. Thank you and hello everyone. So my name is Ulysse Rancon and I will present you my master's thesis that I did with Javier Cuadrado Anibaro, Benoît Cotreau, and also under the supervision of Timothée Masquelier. So I just graduated and I'm just starting my PhD. So I would like to thank so much the organizing committee of SNUFA for bringing us all here today. So without further ado, let's get started. So what it will be about is basically a spiking neural network architecture for a large-scale regression task, which is the estimation of depth from neuromorphic event data. So it's in the computer vision setting. So first of all, let me remind you some use cases of spiking neural networks. So for 3 years, they have been, we have tackled a lot of classical machine learning problems with them. So because of the emergence of this very effective training rule and training algorithm, which is surrogate gradient descent. And so we now have very effective neural networks, spiking neural networks on ImageNet. We have DeepResNet. We also have spiking detectors as well. I've heard there's a version, a spiking version of YOLO. And also, I know that there are some motion segmentation neural network models. But as you can see here, all of these tasks are more or less in the classification family of tasks, I would say, because in either case, you're doing a classification. So here for classical classification, you're doing it on the full image, or on one part of the image, on an object, or you're classifying each pixel. And it appears that there have been very few spiking neural network architectures for the task of regression, and especially at large scale. So it's not so surprising, because I would say that SNNs and regression are not a good match at first, at least, because it's very hard to regress real values with a finite sum of real values. So that is a discrete weighted spike train. So you have your target value here. You can imagine it's a target potential of a readout neuron. And so this output neuron, this readout neuron, integrates the weighted action potential of its preceding synapses and must match the target value. And so it's particularly difficult because so the preceding spike trains are discrete, and you have a fixed number of synapses, so a fixed number of parameters preceding your neuron. And if you want your SNN to be effective, so if you want it to be sparse, then the number of terms in this sum should be as low as possible. And an illustration that I like a lot. I don't know if you know this game. So in France, it's called Numbers and Letters. I think in the UK it's called Countdown. But basically, a participant, it's a TV show. So the participant must approximate the value at the top with a small set of numbers at the bottom, with by doing some elementary operations. And it's exactly what the SNN is doing, actually. So except it is doing addition, so accumulations of spikes, or subtraction of if the weight is negative. But it's doing exactly the same, and these numbers are the synaptic weights. So actually, in fact, the SNN for regression is playing countdown. So now, with that explained, let me just remind some of you, for those who don't know what a dynamic vision sensor is. So they are also called the event cameras, and these are a new kind of sensors, which are biologically inspired from the retinal ganglion cells of the visual nervous system. And so they are very promising because they have very interesting features in terms of temporal resolution, of energy efficiency. And they are very different from conventional cameras because instead of producing a frame at a regular time interval, they each pixel is independent from each other, and pixels produce asynchronous spike trains. And so it happens that we have online a data set which is called MVSEC, which was shot by two of these DVS cameras, so next to each other, on a moving grid, so on a drone, on a car. And there was also a LiDAR to capture depth at a regular interval, and that provides a depth ground truth. And so here we have all the ingredients necessary for the recipe of a supervised depth estimation. And so this slide sums pretty well, I think, the scope of our work. So we have a natural scene, again captured by two of these DVS cameras in the context of the MVSEC dataset. Each of these produce a spike train, which are fed into a spiking neural network. And this spiking neural network tries and estimates a depth, so a depth value at each pixel in the scene. So, well, without waiting anymore, let me present you our model, which we call the StereoSpike. So it can feel a bit overwhelming at looking at it first, but it's not, believe me. So it's no more, no less than adapted UNet architecture. So it's an encoder-decoder network. So the first feature that you will notice is that we have two encoders instead of one, because we want our network to be binocular. There are other ways to implement the binocularity, but that has been our baseline for quite some time, and so we decided to present it like so. So like in any encoder-decoder model, we have a downsampling path and an upsampling path. So the convolutions in the encoders, they divide the spatial resolution by 2, but double the number of channels, and the decoder does the exact opposite. We, of course, because we are in a SNN philosophy, we have an alternance of weights, which are floating point tensors and binary activations, so 0, 1 spikes. And as I suggested before on my previous slide, the readout paradigm is exactly the same. So we have as many output neurons than pixels in the reconstructed scene. So these neurons of this neuron pool, they actually bear the depth prediction of the whole network. So let me now introduce you some key features of our model. So first, we use the spiking jelly Python library, which is wonderful. We also use the integrate and fire neurons that were trained with surrogate gradient descent. So as I said, the readout paradigm is that the membrane potentials of the pool of perfect integrator neurons bear the predictions. So these neurons do not spike; they have an infinite firing threshold, and they have no leak. And so you may have noticed that before, but we have some intermediary prediction layers that enable a more faithful and a more precise reconstruction than with a regular UNet architecture. So I'm talking about these prediction layers here. And I will explain in a moment the interest of these layers. And additionally, our network is, we believe, hardware friendly because it has no bias and no batch norm. And we use nearest neighbor upsampling because we believe it's more compatible than bilinear upsampling in the SNN philosophy. And one important detail that I didn't mention now, I'm just mentioning it now, but we do a reset of all of our neurons at every time step. So we have a sort of a feed-forward or stateless SNN. It's okay. I see some remarks incoming. And it is true that we are not leveraging the temporal capabilities of SNNs by doing that. But on the other hand, it's interesting in terms of hardware because doing a reset of membrane potential on a neuromorphic chip, it's less costly than applying a leak. And we found out that a good potential target hardware for our model would be the Akida chip of BrainChip. So here is a demonstration of our model. So we have input. Our input representation is a spike histogram. So we cumulate spikes every 50 milliseconds on a two-channel tensor, and so we are from a spike train. We are going to a more formal and classical computer vision representation, which is common with DVS data. Here is our prediction and the ground truth. So the pixelated aspect of our prediction comes from the lowest level prediction layer. But as you can see, so the information is encoded pretty well and reconstructed well as well. And more quantitatively, we report some near state-of-the-art performances compared to a fully fledged analog neural network, ANN, which uses 3D convolutions. So again, these are some examples. We have you can see that they are doing a good reconstruction, and we might be losing the accuracy because of this pixelated aspect that we should fix, obviously. And I thought that this slide would interest a lot of you because we tried equivalent INN architectures with our model. So we just replaced if neurons by Batchtorm and ReLU, which is common in conventional deep learning. And we found out that the SNN was yet certainly performing worse on trained data, but much better on the test data. And this was an interesting result, and we are very happy. And it's, to our knowledge, one rare, if not the first case, where spiking neural networks show better performances than NENNs on a test set. And this suggests that spikes could be a more generalizable encoding scheme than floating point tensors. As a conclusion, we present one of the first cases of successful fully spiking neural network model on a large-scale regression task, which is the estimation at depth from neuromorphic event data. Our approach, our trick to enable a more precise regression than with a standard UNED is to have several prediction layers doing a coarse-to-fine prediction. And finally, in this particular setting, for this particular problem and this particular architecture, we have better performances than equivalent ANNs at equivalent levels of complexity. So spikes could be a regularization method, and it begs some more research in this regard. And as for the perspective for this particular work, of course, we want to get rid of this pixelated aspect and get finer grained prediction and exploit this the implicit recurrence of spiking neural networks and their membrane potential to capture temporal dependencies. Thank you very much. I will be happy to answer your question. I hope I'm on time.
Thanks a lot. I didn't have to tell you you were over time, so it was perfect. And also very well received. So we have, again, lots of questions.
Okay.
So the most voted one is from Nicholas.
Yes.
Could the worst performance on ANNs be due to some hyperparameter mistuning?
We used actually the same hyperparameters. Maybe that would not be suitable for an ANN. The same hyperparameters would not be suitable. Would be suitable for the SNN, but not for the ANN. But that's what we tried. We tried exactly the same setting, the same learning rate, and that's what we got. But yes, we thank you for this suggestion. We have to find what's going on.
Good. The other one is from Leah. So first of all, great work. Do you expect better performance with the temporal dynamics of the leaky integrate and fire neurons instead of the integrate and fire neurons, even though that might be more hardware expensive?
So yes, so that's a very good question. So initially we wanted to do it with leaky integrate and fire neurons, and so our plan was to have the same readout paradigm, but so we wouldn't be doing any reset at all during inference, and we found out that it was very difficult to learn actually for the network to learn the depth changes and not the depth. So here our network is learning, is predicting the depth from scratch from zero potential. And if we apply the leak and if our network would not have any reset at all, it would only have to learn the depth changes, which are very slight from one frame to each other, but it would be very difficult to learn, and we didn't manage to do it, and that's why we turned towards this stateless SNN.
Okay, and then there's another question that I think connects to the fact that you have a spike in your network. So it's not clear what is the input to the model. It looks like it's event frames, or you mentioned spike histograms. So it looks like you're giving a frame as input to your model. Is this correct?
It's totally correct, and it's my bad for not explaining that. But yes, so DVS cameras they output so spike trains for each of their pixel, and so action potentials, spikes coming out from DVS, they have a polarity, so on and off, depending on the change of luminance that triggered them. So what we do is and they have extremely low temporal resolution. So what we do, we take a higher temporal resolution, so 50 milliseconds, which is a lot compared to the temporal resolution of the DVS. And given one pixel, for instance, we cumulate into two channels, so one for the on events and one for the off events. We cumulate spikes that happen in this time interval. So if you have 5 on spikes that incoming in the 50 milliseconds time window, then at this particular location, at this particular pixel, then the spike frame would have a value of 5. I hope that was more clear.
Okay, but how is that then converted into a spike that goes as input to the spike in your network?
So
there's something I'm missing there.
So it's the input of our with this representation we have a tensor which is exactly like an image, but has only 2 channels instead of 3 for RGB. But it's exactly the same. So we can do standard techniques of computer vision like convolutions and so on, and it's not a problem.
Okay, thanks a lot. So I think this is the end of the first session of the workshop, and we can go and have a break to start kind of freshly new for the second session in half an hour, right? Yeah. So thanks again to all the speakers of this session. Thanks for Friedemann and Dan that were behind the scenes managing everything to run smoothly. And we'll meet again at 4. Thanks a lot.